Hello everyone, welcome to this tutorial. My name is Xarray. I'm a Google Earth Engine specialist. In this tutorial, I'm going to show you how to reconstruct the daily NDVI using Savitzky Golay filter. As you can see, the daily NDVI highly suffered from the missing pixels and cloud contaminated pixels. But thanks to Savitzky Golay smoothing method, we can reconstruct the daily NDVI values while keeping the phonological variation. And this is the main benefit behind this algorithm for the NDVI reconstruction, and it is really popular in the remote sensing community. I'm going to show you how to apply this technique on a spatial and temporal side of NDVI. As you can see, the first NDVI in a spatial side, you can see highly suffered from the cloudy pixels and missing values, but all of them reconstructed thanks to Savitzky Golay filter that I'm gonna show you how to use this in this tutorial. Okay, make a new notebook in the Colab environment. I'm gonna show you how to do this process in the Google Earth Engine platform using Python API programming technique and XEE library. There it is. Okay, let's import essential libraries for dealing with satellite data in the Google Earth Engine and Python environment. Start with EE and GEE map. Then we need Xarray library because we want to convert our data to a multidimensional structure. Xarray imported as an XR. The next library is the XEE library. As it is not built-in library in the Colab environment, we need to install and then import, just like this. Sorry. The XEE library, as you can see in the right side, is a kind of library allowing us to integrate Xarray and Google Earth Engine image collection formats. And this combination extends our abilities for machine learning data analysis on Google Earth Engine related data, and that's really empower the researchers for the Earth observation data analysis in the environmental science. Okay, now I'm gonna show you one of the applications of XEE and also how making integration between Xarray and Google Earth Engine platform. Remember to import NumPy as NP, one of the most important libraries for Python programming, and another one. I think these libraries is enough for now. And the next library is XR Actually, this is a kind of library allowing us to apply machine learning technique on Xarray structure. So we need to install it first. XR and then import XR SciPy dot signal as XRS, just like this. Let's run the cell and wait until the process is done. You can see all libraries importing one by one. Okay, once the importing process completed, close the messages and then make a new cell. Now we need to establish a bridge between Earth Engine and Colab environment. Earth Engine dot authenticate first and then initialize your Earth Engine account information. So, two arguments necessary here: project and OPT URL. If you search on your browser about XEE and Google Earth Engine, you will find a GitHub page including detailed instruction about Xarray library. In this page, you can find the OPT URL address without any challenge. Just copy and paste it into your code. And the next item or argument here is about the project. Let's go to the code editor environment. I'm gonna show you how to find the project name for your account. Okay, let me reduce the size of this page. Once you go to the code editor environment, as you already have a Google Earth Engine account, in the upper right side here you can see the account information highlighted here. Go to project info and then you can find cloud project name that is associated with your account. For example, for me, the actually highlighted here, and then you can find yours from this technique using this way. So once the authentication information imported, let's run the code, and now Colab asking us permission to access to your Earth Engine account. The permission granted by clicking on account, and so something's wrong. Initialize, there is a typo here. Just like this, let's run again, and you can see the problem is solved. Okay, in the next step, as I address it on my YouTube channel in the other tutorials, whenever you want to deal with the satellite data, the first step needs to you need to specify or define your region of interest. So I'm gonna call a user interface here to select the region of interest easily. So make a new variable map sets to from GEE map library. Let's call the map just like this. The map will have a base map based on a satellite view. Let's print a map to see the user interface. Here you can find your region of interest easily without any challenge. Remember that this tutorial extendable to all around the world and not limiting to a single location or a single kind of satellite data. For example, as I'm an Iranian person, actually I would like to select a part of my own country for this tutorial. For example, northern Iran is one of the areas actually covered by dense vegetation cover and agricultural fields. You can see highlighted here. Using the drawing tools available here, I'm gonna select my region of interest just like this. So in the next step, I need to have this area as a variable in the code. ROI sets to from map, select the last feature as a geometry. From now on, the rectangle actually called as a ROI and available as a variable, and we can bound our data to this region. So the next step belongs to calling NDVI data. We need to use daily NDVI satellite in this tutorial because I'm going to show you how to reconstruct missing information in the daily NDVI data. Okay, open your browser and type Google Earth Engine daily NDVI, just like this. Here, scroll down a bit and then you will find Modistera Daily NDVI available here. These dataset available from 2000 to 2023, including the NDVI data with 500-meter resolution. That's a good option. So, copy the collection snippet into your code. Make a new variable NDVI collection sets to, make a parenthesis, and paste the image collection. Now, filter your data to your target year. For example, I'm gonna work on NDVIs for 2020, just like that, starting from 2020 and ending 2021, just like that. Let's make a print. So NDVI collection. As you can see, 366 NDVI is available for 1 year. That makes sense because the frequency is daily. Here you can see each feature separately. We have one band including the NDVI and some properties such as the system time start explaining the data acquisition for each image. This is the image collection structure. And now in the next step, I'm gonna convert this image collection into the Xarray structure. As you remember earlier, we actually already called Xarray library to convert our data from image collection into Xarray structure. NDVI dataset from Xarray open dataset NDVI collection. So based on EE engine CRS EPSG 4326 and region of interest sets to ROI. I forgot to say the CRS refers to the coordinate system and EPSG 4326 is a unique ID for WGS84, the actually well-known coordinate system in the geodesy and also spatial science. The unique, the CRS value for WGS84 is same for all around the world, and it's not changing by location. So the next thing is about the pixel size here. The pixel size should be imported with a degree format. 1 degree sets to 100 kilometer and 0.005 means 500 meter. So just like this. Let's run the variable and NDVI dataset is ready. You can see from now on actually the image collection exported into the array word, and now from now on we are using Python libraries to handle the satellite data collected in the Google Earth Engine platform. So we have a multi-dimensional structure here: time, longitude and latitude, as you can see. The one dimension explaining the temporal variation, another dimension longitude variation, and another one belongs to the latitude. We have one variable named as the NDVI that shows normalized difference vegetation index for each time and each location. So let's have a preview from the NDVI for the region of interest. So for example, I'm gonna make a subset from the NDVI using .cell. Actually, the cell is a kind of function available in the Xarray library, not in the Earth Engine. So now I'm gonna actually select a part of temporal dimension. We have a time dimension, and I'm gonna select, for example, one single mount for the visualization. From NDVI DS, select the temporal dimension .dt.mounts. Bring images for mounts number 5, for example May. So now let's run, and you can see 31 images selected, and all of them belongs to May 2020. Then I'm gonna actually plot the NDVI variation for this period of time. X sets to longitude, Y sets to latitude. The plotting actually needs some arguments such as x-axis, y-axis, and also time axis. call wrap sets to 7, as we want to have a multi-frame plot here. So I need to show, or I need to have at least 7 plots in each row. So robust sets to true to avoid impact of missing values for the visualization purpose. So, and the next one, the color map. The color actually a combination of red, yellow, and green is actually one of the well-known color map used for the NDVI. One thing is missed here, and it is the variable name, that is NDVI. Let's run a code, and after a few moments you will have a multi-temporal plot that shows NDVI variation over the region of interest. Green colors showing vegetation cover, and the red colors showing no vegetation cover or cloud impact. As you can see, the cloud impact actually uh, the cloud impact is very strong in the daily data, specifically for the regions located in higher latitude areas. So, what we should do in this situation, because several information and data through the time missing because of this challenge. So, a Savitzky Golay filter is a useful method that helping us to reconstruct the missing value, specifically in the NDVI. While we are reconstructing the missing values, actually we can keep the NDVI behavior through the time. So let's plot the average NDVI variation over this region. So here the variable name was NDVI dataset, NDVI dataset. Now I'm gonna calculate its average over longitude and latitude over spatial dimension. Then now the average calculated, then select the variable and make a plot just like this. So here you can see the NDVI variation for this area, and the impact of the cloud cover actually demonstrate highly affect on quality of NDVI values, and very large and big drop occurred because of this impact. So accordingly, the data reconstruction in this case is very important, specifically when you want to study phenological cycle for vegetation data. So, in the next step, I'm gonna show you how to use Savitzky Golay filter to do this process. Okay, the variable was NDVI DS, including the NDVI for 2020. So let's make a copy from this array data. From NDVI DS, I'm gonna make a copy, and from now on, I'm gonna work with a copy of the previous data, because I'm gonna keep the original data safe and use a copy of the original data for the rest of processing, because I don't want to change the characteristic of the original data sets. Okay, let's run. Remember that the NDVI DS2 and the NDVI DS, both of them actually showing same information. Just this is a simple copy from an original data set. Okay, here you can check it out. NDVI DS and NDVI DS2. Everything is same in these data sets. Okay, in the next step, we need to change the time dimension, or we need to replace the time with the numbers. So, how to do this? First of all, we need to save the time dimension data into a single variable. NDVI time sets to From NDVI DS2, select time dimension and get values and make a copy just like that. If you print the NDVI time, you will see this equation, this variable, including the temporal or only the date of each NDVI values available in the NDVI DS2. Okay, so in the next step, we can replace the time with the numbers. Here in the NDVI DS2, let me to show you the main data set, then I will explain what we want to do. As you can see here, we have multi-dimensions. The one dimension is time, length, and lat, all of them actually available on their coordinates. So that's why from NDVI DS2 and from chords or coordinates, I'm gonna change the time information or replace it with the numbers. So dot chords, because time available under coordinates sets to okay. From numpy dot arrange actually making a range of values based on the number of the times we have in NDVI DS2 dot time. Let's run, and then you will see that the temporal information replaced by numbers here. There it is. Okay, now our data set is ready to actually apply Savitzky Golay filter on. So NDVI smooth, a new variable will be created in this process. From XRS, XR SciPy, call subgoal filter, just like that. You can see the arguments description in the right panel. So the first one is the variable name. From NDVI dataset number 2, select the variable. The next one is the window length, shows the length of the filter. So for example, here we are dealing with the daily NDVI. The length filter, the temporal filter or temporal length here, let me to enter window length. There it is. Okay, for example, if you set 30, meaning that you want to keep the monthly variation of NDVI after a smoothing process, or if you set it to 7, you want to have the weekly variations of the NDVI over your region of interest. The longer window makes a smoother result, and also with the lower uncertainties and lower noises. It's totally up to you which window length is going to utilize in your you want to use in your study. For example, for my study, the variations or the monthly variation of NDVI is fine. So I will set NDVI length or filter length to 30 days. The next thing is the polyorder, the order of polynomial function. So the polyorder typically is number 2, and the next parameter is dimension. The dimension should be time. Let's run a code, and you can see the NDVI smooth is created. Okay, you will have a smooth NDVI, but there is a problem here. We need to actually return dates information back. That's what we need to do in the next step. Okay, now go to the NDVI smooth in the chords and find temporal information that is a value for now, just only a string integer numbers, and it will be equal, or it will be set to here NDVI time information already stored in this variable NDVI time, but it was wrong, there was a typo. NDVI time. Okay, let's print the NDVI smooth again, and here you can see the temporal information, the correct one, replaced. So, and now we can actually do a comparison for average and also for the spatial dimension here. So let's make another subset. For example, we can actually repeat the previous analysis or visualization, this time for a smooth variable. So select the same mount, no need to select the NDVI because the value is already available. Just make a plot. X longitude, Y latitude. The variable is also NDVI smooth. Yes. Call sets to time. Call wrap sets to 7. Robust sets to true. And CMap sets to red, yellow, and green. Let's run. Here you can see the reconstructed NDVI that shows the daily variation with a better accuracy and lower uncertainty. Okay, as much as window length increases, the lower number of missing values remained. So, in the next step, we want to get average and compare it with the plot variation. So, bring NDVI smooth and calculate average over temporal dimension, longitude and latitude. Make a plot then. No need to add extra arguments. Just run, and here you can see the daily variation of NDVI, and it is smooth based on monthly NDVI variations. So I hope you liked this tutorial as much as I did, and I'm asking you to share this tutorial with other people who are interested to remote sensing and dealing with Earth observation satellite data. The code link is available below this video on my YouTube channel in description box, and you can ask your questions and compare your code with mine. Thank you for your attention.